My name is Gil. Feel free to ask any questions during the talk. Today I'm going to expand on what we talked about yesterday and actually getting into some of the proofs, at some high level, some of the proofs. The first thing I need to do is to actually kind of formally define the zigzag product, because otherwise we can't even start. And as hinted yesterday, the zigzag product doesn't operate on graphs. It operates on kind of the labeling of the graph. So I need to talk about that for a second. It's a minor technicality, but I have to do that. So let's start with this. It's actually very simple. So let me just say you have a d-regular graph. So, this is a vertex. It has its d neighbors. And you see already, without even noticing, I kind of labeled the neighbors of this vertex v. So v, for example, can consider this vertex u as its first neighbor. Okay? And u doesn't have to kind of agree. It can think of v as, I don't know if it's fourth neighbor or something. That's what I'm trying to just define here. Okay? Nothing else. Just kind of labeling the neighbors of a given vertex without worrying about consistency whatsoever. So to do that, let's define the rotation map. Our rotation map. So pi g is this function that, given a vertex and a neighbor number, produces the vertex that produces a vertex, and also sometimes we do want to know how this vertex considers that vertex back. So for example, that's our definition by example, pi g of v1 is u4. Okay. That's the definition. And you know that this is an involution kind of by definition, right? Because by the definition of this 4, when you apply this pi g to that, you get this back. Okay.
Definition is that it's an involution, or
by definition, it's an involution.
By definition, yeah. So what was the question about?
It's part of the definition.
Yeah, but right. I mean, the definition is that this number is such that you consider v as that neighborhood. Right, so that's an equation. And that's the way back. Good. And with this, we can define the zigzag product. So the zigzag product requires this pi g and pi h rather than the adjacency matrix of g and h. This is more information, right? But I think of it as kind of arbitrary, at least for these talks. I mean, sometimes you have better labeling.
Sorry, I'm slow. Would you repeat again? What is pi sub g?
Yeah, so pi sub g is this function. So it's this function that given a vertex and a number, so the first, projected to the first coordinate, you get that vertex, in this case, the first neighbor of v.
That's a u. It's u comma 4.
Yeah, it's bad u, right?
Okay, now I got it.
Yeah.
Thank you.
Right. And pi g of u4 is v1.
Just to be clear, you're saying this labeling is kind of arbitrary, but the zigzag product is going to be different for different labels.
That's true.
Okay, so
Yeah, that's a good point. I mean, the zigzag product will depend on the labeling, and for the same pair of graph or the same G and H, different labelings will produce different bounds on omega. The labeling is actually important, but our theorem holds for every labeling. So that in that sense, I don't mind about the labeling that much. I would say that a consistent labeling is a labeling such that this number is the same as that one. For example, in Cayley graphs, you can have those things, or if you take the union of D matchings, you can consider the first matching, the second matching, and the diff matching, and then you get kind of consistent labeling. Namely, we consider the V and U agree on this number. It's actually bad for. It's not random enough. It's bad for the zigzag product. You actually would prefer more kind of random labeling. I mean, you shouldn't worry about that too much for this talk. Maybe for the next talk.
the upper bounds, they are going to be of the form. There exists a labeling. So
Yes.
This is a zigzag product for that labeling is going to have a nice upper bound.
Exactly. Right. And that's required. There are labelings for which the upper bound is actually bad. The bound, the actual answer is bad. Good. So let's define the zigzag product. So you are given two graphs, and actually the position maps of these graphs, but G is going to be to have a vertex set VG of size n. If I'm saying n, I always mean the size of this set. And it's going to have an edge set, which I don't really care about because I'm anyhow going to specify the labelings. But some vertex edge set is going to be D regular, n vertices, and it's going to have its own pi g. You actually specify pi g, not g. And you also have this h. C regular. It's going to have D vertices, and it's going to have its own rotation of pi h, pi sub h. And now I need to define the zigzag product. I'm going to use the second board for that, of course. It's going to be approved by picture, but this is a new graph. Its vertex set, if you remember yesterday, is the product set of the two vertices. And you should think of it, as follows. You should think of every vertex in G, little g, you should think of it as a cloud that contains D vertices, one for every vertex in H. Okay? But it's just not formal. And now there is also an edge set, but I'm going to do better. I'm going to tell you what's the rotation map, so you can infer E. And the rotation map I'm going to draw for you. Okay? So maybe let's move here. But in order to say the rotation map, let me kill the tension and say that this is a C squared regular graph, if you remember from yesterday. I need to tell you that number so that I can define this pi. So pi of the zigzag product, right? I need to take a vertex, which is a pair G comma H, little g comma little h. That's a vertex in the zigzag product graph. And I need technically to take a number between 1 and c squared, but allow me to take two numbers between 1 and c. It would be nicer. Let's call them A and B. So A and B are elements in C. And I need to produce to you G prime and H prime. That's kind of the first coordinate. And I'm not going to produce the second coordinate because I'm lazy, but you will understand what the second coordinate, namely what is the A prime and B prime that will get you back from G prime H prime to GH. Also, just not to confuse anyone, let me go back here. I'm going to denote by pi G dot, just the lazy version of pi G. So just pi G projected to the first coordinate, only the vertex. Okay. I do need, for the zigzag product, I need the entire thing, but pedagogically, it's nicer to work with this dot version. Okay, so given G and H and a pair A and B and C, I need to produce these numbers, and by that, I actually kind of defining this thing.
I don't understand that definition. What is pi g dot?
It's just pi G restricted to the vertex coordinate.
The output, not the
The output, yeah, sorry, the output.
Okay,
I'm not going to tell you how to go back because
okay.
because we all understand that anyhow. But I do need the entire definition even to define this. That's the kind of annoying thing about it. So here is the definition. It's very similar to what we had yesterday, but it's now formal. So I draw this circle. What I mean by that, this is the cloud of G. There are D vertices here, one for every vertex in H, and this is little h. So we are starting in this vertex. This is technically G comma H, but I like to draw it like that. So cloud G vertex H. For another G prime, there is also a G prime vertex H there. And now, given A and B, I need to tell you to which cloud do you go, and at that cloud, at which vertex. So the first thing you do, you kind of ignore G. You look at H, and you take, you see A is a label for a vertex, for a neighbor in H. So you can go to the eighth neighbor of H. I would call it H prime, but H prime is going to be the end result. So let's call it H double prime. And let's look at this vertex. This is H double prime, which is, the lazy version of the rotation map, starting from H using A. So you start at H, you ignore G, you completely ignore where you are living at which cloud. You go to the eighth neighbor of H according to the graph H. There is also a labeling back here, but I'm ignoring it. Okay? You would need that if you want to go back. Okay, so now we are at this vertex. The next thing we want to do, any guesses? But not Aviv. So you can, this is the H step. Now we need a G step. So the second step that you're going to do is you're going to, I mean, H double prime is a vertex in H, but it's also a label in G. So you're going to kind of look at it with this hat in mind. So you're going to go to that neighbor of G in capital G. Okay, so you're going to apply the rotation map of G now. And so maybe let me do this. So what you're going to do is you're going to apply the rotation map of G with G as the vertex, H double prime as the neighbor number. And I actually do want to know how do I go back from it. So we are going to go to the vertex G prime. That's the final G prime that we are going to get. So this cloud is cloud G prime. And I do need to specify the way back. So let's call it H triple prime. Sorry for that, H triple prime. So
You saved H prime, but
yeah, I did my homework, so I knew.
I don't understand, H is an element of the vertex set of big H.
But
We plug this into pi G.
right, exactly, because that's the cool thing. It's a vertex in H. With the perspective of H, this is a vertex. But with the perspective of the graph G, this is just a number between N and D. Or you can associate it with numbers from 1 and D. If you kind of identify VH with 1 to D, with the set 1 to D, which maybe I should have said. Right, maybe that's a confusion. This is a graph of size D, so I somehow in an arbitrary way associate this vertex set with the set 1 and 2D. And now this, you can think of it also as a labeling of the graph, a label number of vertex of G.
That's why you take the size of H to be the degree of G. They are in 1 to 1 plus 1.
Right, so it's right. Technically, I should put on some isomorphism here, but rejection there. But
So is this diagram commutative? Like if I now start at this point that you end up with and I apply the same.
right, not yet. Right, so that's what. So right, so I need one more step, and then it's going to be. Yeah, right. It will give you a symmetric. But right, good. So it's not. Well, it didn't end yet. But what's important to note is that even though I just want to define the lazy version of pi, I'm really going to need a non-lazy version of G in this case. Okay, so we are at this vertex, and then we ought to use kind of B here. So the last thing we do to get H prime, which is the last thing I owe you, is we are going to look at the beef neighbor of H triple prime. So H prime is going to be pi sub H of H triple prime with B. And indeed, if you are here, there is some B prime that will get you here. When you do that, that's an evolution. And then there is some A prime that will get you there. And that's the B prime, and you should revert it. And that's the B prime, A prime that you need to go back. Yeah. So is this clear? Like if you do the pseudo-analysis, you've seen it like 4 times in your life. But like, if you haven't, then it's not clear why this is the construction you would think about. And I'm not sure it's even if you did it, but you used to it. So that's part of your education. Okay, so good. So we want to work with operators. So let's try to write it in operator form. And then at that point, you can kind of forget about the actual combinatorial definition. So this is a little bit observation. If Z is the adjacency matrix of the zigzag product graph, so it's an ND by ND matrix, right? Then you can actually express it as follows. Let me just write it for a second and then I'll talk about it. This dot has kind of nothing to do with that dot, by the way. This thing, so, okay. So what's going on here? So if you multiply from the right, doesn't matter, but if you multiply from the right, what you see is that this operator, which is just I tensor to H, namely you operate according to H in every cloud of G, n is the number of vertices in G, this operator tells you that you apply the adjacency matrix of H in every copy. So that's kind of the 8th step. Right? If you plug a unit vector, you can see that. And then now this matrix, should somehow encode pi G. And that's exactly what it is. This is an involution matrix for pi G, namely G prime at, so this is a matrix ND by ND matrix. So at this entry, like the GH comma, this is the row and column, GH comma G prime H prime, you just have a 1 or 0, depending on whether or not pi capital G of GH is G prime H prime. It's just the adjacency matrix of the involution.
Multiply representation.
Right. Yes. I don't think we ever use from here on that this is an involution. And then that's the B step. Right, so it requires a little bit of a proof here that that's adjacency matrix, but at least intuitively it makes sense that you apply an H step independent of the cloud that you're sitting at. So that's the I tensor H. Right, the first step has nothing to do with G, little g. So it operates the same in every cloud. Then you do the involution, that kind of, things go inter-cloud kind of movement. And then again, independently of where you landed, you apply again H. Okay. And just because I'm shooting at some particular formula in mind, so let me also notice that you can write G dot as P transpose MP, where M is, your favorite fixed involution on the set 1 up to ND. So maybe M is the kind of the matrix corresponding to this involution and some fixed involution. Okay? And P is a permutation matrix on ND. Just renaming of M. But you can get any involution by just renaming that involution. So,
Full supported.
sorry?
Not any involution, full supported.
Right, perfect matching, or that's how you should call it. Yeah, good, that's true. My guy always fixes me about that, but it's right, like perfect matching, no isolated, no subgroups. Perfect matching. Right, so any G prime can be written like that. That's what I'm saying. Anything like that gives you a G prime.
I mean, you could just take P to be the identity, permutation.
Yeah, right.
And the labeling.
Like I just want this to be I want the information about G to be in this, not in that.
Oh, you're saying M is fixed, it's just,
Right.
I see.
Like it's nothing, just a relabeling, but I like the fact that now the information about G is hidden in P, not in M. It's nothing deep about it. It's just going to be nicer to look at it. You'll see in a second.
But it would be nice to have a way of separating the graph structure of G from the choice of the labels.
Right, exactly. So that's essentially what it's saying.
So where's the graph structure of G?
It's actually in P.
I see.
Right.
It doesn't matter, you need only that it's a permutation.
Right. Yeah, that's true. Yeah, but you'll see in a second. It'll give you like something nicer to look at. That you can skip this step. I like this step.
Oh, no, but I have a program, rather than.
I know.
Doing what you.
I know what you.
And the permutation, but then I have to
Right.
take the graph part, the structure of G into it.
Right. I know what you're doing there. Yes. Okay. Let's call this thing like nice H, or I don't know, fancy H, just to save some time. Fancy H is just I tensor H. So what we just said is that the zigzag adjacency matrix is given by H, P, where did they put the transpose, and PH. Right? And you can call it this sub P to emphasize the fact that it depends on P. That's the only thing. I mean, H is kind of given for us, so I want to stress the P part of it. And with this, what we want to prove, now comes from the fun part, we want to prove, so this is the question that we ask, does there exist a P permutation over S and D such that lambda 2, the second eigenvalue, for me this is the second largest root if you don't mind, of the characteristic polynomial of ZP is bounded. Oh, right. So I'm kind of starting without noticing even with the upper bound. So, right. So, you know, for the upper bound, for the lower bound, you need some figures, but for the upper bound, what you kind of want to prove is some bound on this thing. I'm going to remind you the theorem statement, don't worry, but if you want to prove an upper bound, then what you want to show is that for every h there exists a g, namely for every h there exists a p, such that the second largest eigenvalue is not too large. How large? The thing that we had yesterday, and I will remind you of that.
We want to prove that upper bound that exists for every. There is a bound already for every P on this number, and now we want to improve it for some.
Right, yes, exactly. Like for every h and for every g, and then for every h and for every p, there is the RVW bound. Now I want to prove the bound that we talked about yesterday. I'm going to remind you of that. I just completely forgot about actually stating the theorem, so I'll do it in a second. What I want to prove is that there exists a permutation matrix, there exists a G, namely, that gets you the upper bound, the bound that we talked about. It's both upper and lower, the actual right number. But, sorry, that's my bad. I need to remind you what is this thing. So maybe let me continue one more line here and then we'll do it. But generally what you want to do is to prove an upper bound for the upper bound case. And an upper bound is this thing. And before reminding you of that thing, let me just tell you where we are going. So what we are going to do is to do a kind of probabilistic method argument, but not really, like an MSS style probabilistic method that doesn't talk directly about the second largest eigenvalue of this.
The eigenvalue, it's the root.
Right, so the second largest eigenvalue of this operator.
The root.
I wrote it like that intentionally because of what's coming next. Usually you just write lambda 2 of the operator. I wrote lambda 2, namely the second largest root of this characteristic polynomial of Z. Just because something that will come next will be easier to compare with that. So what instead we are going to do, and that's a weird thing.
I'm still confused what you're given and what you're allowed to choose. So you're giving H, right? H is what it is. Now, you're going to choose both G and the labeling like a pi G?
Right, so we're going to choose the labeling of G, which defines G.
Yes, but the edge set of G is given to you, or you're also allowed to choose that?
No, I'm allowed to choose that.
You're allowed to choose that too, but the degree of G presumably is fixed.
Right.
And where does the degree of G enter in this formula?
So pi G and the adjacent matrix of G is determined by P.
Yes.
And even that structure, the way you partition these two blocks, ND by ND blocks, that's kind of the degree of G.
So you're saying that really I'm allowed to choose any permutation matrix
Yes.
here and it will already satisfy all my constraints.
Exactly.
It's not immediately obvious to me.
Right, that's true. That's essentially hiding the configuration model, really.
Okay.
Rather than what happens in Friedman or right. Here it's easier to work with that rather than some of. But okay, so maybe I'm so sorry. Just to make sure, we're given H. P encodes the actually pi sub G, and therefore G. Right? And you are allowed to choose a P, namely G and its labeling. And the main step, which is very weird, I mean, that's what you want to prove for an upper bound. And that main step is the proof structure, the proof framework comes from MSS, Marcus Piemann-Srivastava, is to look at the expected characteristic polynomial and talk about its second largest root. So what we are going to do, we are going to look at this view. So maybe let's clean this up a little bit. Lambda 2 of maybe too many of those, right? Lambda 2 of the expected characteristic polynomial. And we are going to bound it by the same expression that I didn't write here. Just a second. Hoping that a bound on the expected with respect to the expected characteristic polynomial will give you a bound on a particular permutation very much like a probabilistic method. You bound the expectation of a random variable, you get a bound on a particular point in the sample space.
So would you take this expectation over all permutation, right?
Yes, right. So this is P completely uniform in SND.
So I'm also a little confused what you gain by going to this quadratic polynomial working with permutations rather than just working with a linear polynomial of matchings. You could just take the average over all random matchings.
Right, actually, that's very interesting. It would have been helpful for us, but we don't know how to prove that matching is enough. Like perfect matching is enough. We do need the whole permutations. I can point out that where things break when you don't do that. This is closer to Haar orthogonal than matching. That's kind of.
So a uniform random matrix associated with uniform random matching is not going to have the same distribution as P transpose P, P where P is uniform with permutation.
So we certainly cannot prove it, and if I remember correctly, experiments show that it's not the same.
But this, it doesn't make sense to take P and involution. You already
You started with an involution.
embedded. You're just this and code taking a random involution, a random perfect matching on the whole.
Right, that's true. It's not enough for labeling.
No, but you're saying that these two things are different.
Right.
That's exactly my question.
No,
They
it-
look like they should be the same.
Instead of taking a whole conjugacy class, which is what it's doing, you will take a subset of it then.
Yeah, so it's not clear if it is enough or not, but
No, but it's not, I mean, mathematically, it makes much more sense to do. This is a uniform on the conjugacy class of irregular graph.
right, that's another distribution that you are saying, in which the relabeling is done in a kind of a matching kind of way.
This is, like you said, it's a project configuration model. And you could have taken a subset of the configuration model. Nobody judged that they should.
So when we get to the quadrature step, in which I'm going to say something about why permutation is good enough, then we can maybe get back to this point. It's a very interesting point for us. In order to make this explicit, it would have been better to have an involution here, but it doesn't work. So just. But you look at this thing, and there are two things you should worry about. First of all, and that you should trust, not me, MSS. It is a good step to do. Namely, if you bound the second largest root of this polynomial, the expected characteristic polynomial, we call it, then for some reason it should give you a bound. Otherwise, I wouldn't have said that. But there's something more basic that you should worry about. Who said that this is a real rooted polynomial to begin with? Right, you look at this polynomial, it's a sum of polynomials, you divide by sum of polynomials. If you sum real rooted polynomials that are kind of general position, you won't get a real rooted polynomial. It's an untypical setting. So who said that this is real rooted? It's not a priori clear that this is a real rooted polynomial. Right, you can take two parabolas, you add them up, you don't get a real rooted polynomial, unless they are like that. And so therefore, it just it doesn't compile lambda 2 of what does it mean lambda 2 even? What's the second largest root? But it turns out that it is real rooted, and the buzzword for proving that is interlacing. Okay, so it turned out that these polynomials, this set of polynomials, has some structure as a family that guarantees that essentially any expectation of them, not just uniform, is real rooted. It's a very nice theorem, but I won't be able to talk about it now. I'll be happy to talk about it offline. The way I think MSS proved it is using real stable polynomials, but actually you can do it only with interlacing. It's actually easier. And for the same reason of interlacing, and in fact it's kind of the proof goes together, you can prove that there exists a permutation for which indeed, if this is bounded by some number, then that's bounded by the same number. This is essentially bounded by that. So there are two things that interlacing, and that's a buzzword I'm not going to get into. Interlacing just means that this polynomial family has a structure, a certain structure. So there is this buzzword that kind of tells you that it's not just A and B, it's kind of combined, but yes, this is a real rooted polynomial, and lambda 2 of that expectation bounds lambda 2 for one of the permutations in the family. So I'd be happy to talk about it some more, but I won't be able to focus on that.
You are saying they are interlacing, or you are saying that,
Good, yeah, good. So they are interlacing. That's something that actually we had to prove because it's not the MSS problem. We have this G in the middle, H, sorry, in the middle that bothers us. But for every H, this will form an interlacing family, so good. And then using, we actually also had to kind of play around with the actual proof, but using the MSS proof about interlacing, you know that once these are interlacing, then what I said holds. This is rooted and for some P.
What goes into this proof?
Right, in 2 words, it's just, right. So,
Sentences I'll give you.
right, so it's a negotiation part stuff. So yes, actually it's a really nice thing. So kind of what you do is you look at the coefficient space, right? The expectation here is in coefficient space. Right, I mean, you sum polynomials and divide, so each coefficient is getting averaged by itself. So you're looking at the end of this coefficient space, let's call the degree D. So technically it's you look at coefficient space and you have this polynomial sitting here. Right, for every P you get a different polynomial. These are polynomials in degree n times D. This is n.
Yeah, you want S sub D, but you mean S sub ND.
It says there's a tiny
It's a-
n.
There is a little n, yeah. Right. It's a sum of a sum, right? So you have this polynomial sitting there, and each of them is real rooted. Now, if you think about it, if you look at the discriminant essentially, or then you know that there is this kind of manifold of, let's call it double root manifold. There is a name for that, discriminant or something. But there is a test, right? You can take I forget the name of it. You can take a polynomial and its derivative, the resultant. You can look at the resultant of the polynomial and its derivative. If it is 0, it means that you have a double root. So this means that there is a polynomial equation in the coefficients of the polynomial that is 0, that polynomial is 0 when you have a double root. So,
What? Say that sentence?
right, so if you look at a polynomial f, and you look at the resultant, which I'm not going to define, but that's some polynomial, some determinant of some matrix that depends on the coefficients on f and f'. So this is 0 if and only if f has a double root. Or more generally, if you put f and g, if they have a common root. The important thing is that this is a polynomial in the coefficients of f, because they appear here also.
So it's a polynomial equation that decides double root, isn't it?
Exactly.
Okay.
So it's this manifold that it's here, like in degree 2, it's like these two conic-like creatures. And the point is that a real rooted polynomial, so it's some manifold, this is the zero set of this is the zero set of that function. So if you're here, then you have a double rooted. Now, in order for a real rooted polynomial to be non-real rooted, you have to go through this thing. Because how can you have complex root if you start with, if this is a rooted polynomial and this is a non-rooted polynomial, and you look at kind of the interval between them, the polynomial and the complex combination, you have to go through this thing in order to move from real rooted to non-real rooted. Because it means that two root has to kind of combine together and then go to the complex plane. And that's kind of how it works. And then what you show is that this interlacing property, it talks about a third polynomial that interlaces both, but what really goes on in this geometric sense, it means that, there is a way of connecting this set of polynomials. That's actually a big picture because there is no way to do it in this picture. I think that Adam Marcus liked this picture. So I'm just going to steal his picture if you don't mind.
Because this resultant equation is degree 2?
No, it's not. It's degree of the polynomial.
Why are you doing this picture?
Yeah, just because it's much more complicated and yeah. But the point is that, this is one, you say you are averaging over 4 polynomials. So what interlacing property means that you can kind of combine the polynomial in pairs like that and kind of evade this manifold. So maybe this is the expectation. So to be interlacing, what it means, this is the expectation of these 4 polynomials. I try to put it in the middle. So this is the expectation. And you can kind of connect all of them simultaneously, but you can connect them in these kind of line segments. and in each line segment choose another polynomial, and here one also that will eventually go and touch the average without ever crossing it. And then what you show is that the max root function is actually monotone on this. So if you know a bound on the max root of this thing, then because you are monotone here, then at least in one direction the max root is going to go down, and then again, and so this maybe it's go like this, and when for this permutation lambda 2 is smaller than. It's really. By the way, I gave a course about this in last semester, and it's recorded on YouTube. So elaborated on that. So if you have some time.
But you don't have a intuitive understanding of it like MSS, where it's the metric polynomial.
Right.
You don't have any, or you.
Right, but I think it's a good thing. I mean, MSS I call it the pre-MSS. That's the MSS before doing they did interesting, but not free probability. So what they did is they completely understood this expected characteristic polynomial. It was the matching polynomial in their setting, and in other setting it's kind of a matching like polynomial. So you can generalize that, but still they had to do this part. So the way we will understand the expected characteristic polynomial is using essentially free probability, but the way that we are going to infer from our understanding of the expected characteristic polynomial to a particular permutation goes for interlacing. And you can describe it as a tree because we like tree in computer science, but this is what's really happening there. And, okay, so I hope I told my debt to.
It's a long 2 sentence.
So let me kind of remind you, or maybe, okay. So let me just remind you the function that we are, this bound, this little rectangle that they put up. What we want to do, so if you recall, we had this function yesterday, given h, we had this function. I'm kind of going to play with it a little bit here now, but so yesterday we had a c squared outside or something. I probably don't remember. C squared outside. I'm kind of removing that. I'm going to look at the non-normalized version. So it's this thing. And recall that GH is the Cauchy transform of H, which you can write in 2 different ways. Either 1 over D, D is the number of vertices in H. 1 over D times, this is the trace of the resolver, right? And these are the eigenvalues of H. Maybe I should put H here, but then probably Ramon won't see it. So, yeah, sorry. And you can also write it as, if you want, 1 over D times the derivative of the expected characteristic polynomial, of the characteristic polynomial divided by the characteristic polynomial. Same thing. So this is the function that we talked about last time, and the bound sitting there that we want to prove is that this equals the minimum when you minimize over this interval. So again, because I feel like made a unnecessary mess, we want to prove that there exists a permutation for which the second largest root of this polynomial, namely lambda 2 of this paragraph, is bounded by that expression that I wrote down. Then the way we are going to do it is we are going to actually not considering a particular permutation, we are going to consider this expected characteristic polynomial, which I assure you is a real-rooted polynomial, and I also assure you that that's enough. You know, bounding this will bound that because of this interlacing structure that you have there. And so the goal that we have in front of us is to bound this by that expression. So that's the minimum x larger than c squared of ch of x. Question so far? Okay, so
Only one.
yeah, please.
So here you mentioned resultant. Was that giving an idea or was it precise? So in a sense that for me it's not clear at all why all the roots are different.
I see. For these
Yeah. I mean, you might have graphs that have multiple roots in
That's
the
true.
spectrum.
So that's true, but I didn't mean right. So you talk about this thing. The double root part?
I mean, that part, I understand that you're explaining this exception, this expected values on each
Mhm.
layers. So that picture I understand. But I didn't understood this, was this a schematic type of argument, or was it precise?
No, it's actually precise. So when I say double root here, I don't mean a double root of this polynomial. I mean a double root of this polynomial. I do mean a double root of this polynomial. Yeah, you're right. Yeah, but I mean, that's kind of living on the edge. If you have a double root, when you're very close, you are at the closure, right, of this thing. You're at where you satisfy this polynomial. If you move a little bit to the wrong direction, you get complex roots.
You perturb it a little bit.
Right. So I should also do these things. That's what you're saying. I agree. They can also sit here. The polynomial can have a double root, but I don't want to go here. The thing is that the max root function is monotone on components that are connected components, induced by this manifold. So if you cross it, then you're guaranteed nothing. I mean, there is no max root anymore. It's going to be complex. But once you are on one side, well, inside one component, you're fine. But I didn't, I mean, that was just, it was way too short of an explanation, right? I'm just kind of saying that. I wouldn't understand any of it if I would have told that, and that's it. Actually, we will need this part. You make it look so easy when you make it. Correct? It's harder when it is. Okay. Are we okay if are we on the same place where we're saying that what you want to do is to bound the expected characteristic polynomial lambda 2 of that by this expression? Okay, so let's kind of massage the expected characteristic polynomial, and then Ramon, hopefully it will be clear why I needed permutation, or we'll see. So okay, so our goal now, in case kind of we got lost, is to look at lambda 2 of the expected characteristic polynomial. P is in S and D of ZP, but let me kind of write ZP so it was H P transpose MP So what we want to bound is to bound this number, and again, you should believe me that this is actually well defined. It's a real rotated polynomial. So, let's forget about lambda 2. Let's just look at this expected characteristic polynomial. Every summand, every element here in the expectation, because the trace is cyclic, because the characteristic polynomial is cyclic, you can move H here. Right? So you can write it as, so I'm ignoring lambda 2 now. So you can write it like that. Nothing happened. And this, by the way, is just like I n tens of H squared. Like it's 12 tens of it, 12 the elements. And the reason I wrote it like that is because you can see there is something that's going on here now. You see, you should think of these P's as kind of trying to, for the lack of a better word, free M from H squared. Like I'm conjugating M by H squared. I have no control over H squared. Right? I mean, it's a graph that was given to me essentially. P is really G, but I think of a random choice of G should somehow free this this matrix, this operator from that operator. In what sense? Like so if you think of H squared, it's a symmetric matrix, it's a normal matrix, so it has a set of orthogonal eigen vectors with some corresponding eigenvalues. And also M. M is a very simple matrix. We can actually see the eigenvectors, but let me just go like that. It's a 1 minus 1 kind of eigenvalues there. And what happens with P is that P essentially relabels the vectors, right? Because it changed 1 to 5 or whatever. But you kind of would hope that P is random enough so that it decouples the eigenvector structure of that with the eigenvector structure of that. Of course, it doesn't really do so, but you kind of hope that this kind of test function would think it is. There's only one little problem, is that there is a structure hidden here, and that's the all ones vector. Knowing all ones vector, because the graphs are finite, so the all ones vector, you see the all ones vector is an eigenvector of each of these matrices, right? Of H squared and of this thing, because, you know, for many reasons, this is a conjugate of an involation or just an involation by itself. So if you want to write the expected characteristic polynomial, each of these summands has x minus c squared factor going out, because the eigenvalue corresponding to eigenvector 1 here is c squared, because this H squared, H is c irregular, and the eigenvalue here is 1. So you get c squared times 1 times some other polynomial. This has nothing to do with. And now, okay, so orthogonal to that structure, you may hope that this is a polynomial which thinks of H squared and M as completely independent in terms of eigenvectors. So let me take a detour and tell you one thing about this, and that where Haar measure will come, and then we can maybe revisit the permutation versus evolution. And I'll actually be happy to hear what you have to say about that. So let me say one thing about that, and then we're going to replace this with something very nice. That's what's going to happen. So say we have two, say symmetric, normal is enough, but say symmetric matrices, A and B. So this is a little bit of a detour, but it's going to be a short detour. Say that A and B are symmetric matrices. If I did, I don't know, I don't really care, but M by M matrices, some unrelated matrices, unrelated size. Then you can do the following. You can ask the following question. Very similar to what we had there, but I'm going to replace these P's with Q's. Q is my go-to name for Haar measure. And I also think the transpose moves at some point. Doesn't really matter. And this is so you can ask the following question. Is there a measure that is kind of random enough so that it is actually satisfying what I said? It decouples the eigenvector structure of A from that of B. I mean, the eigenvalues remain the same, right? You conjugate if you will conjugate by a unitary matrix, the spectrum will remain the same here and here. But the eigenvector structure hopefully will get decoupled, which is, in a sense, kind of a freeness type phenomenon. And indeed, there is such a measure. It's called the Haar measure. So, every very nice group, like a locally compact group, has one measure which is a translate invariant, but it's big words for saying not too much. So you should think of this Haar measure for the orthogonal group as just a measure that kind of rotates and reflects in such a way such that every basis can move to every other basis with the same probability. Doesn't make sense, of course. It's like Aleph in size, but you know what I mean. It's like the measure that makes everything completely random. For example, in 2 dimensions, it's easy, so I can say that. What you do is so in order to generate this group, what you do is you choose a rotation. You can rotate this by any pi that you want, between 0 and 2 pi. And then you can choose whether to reflect around, say, the x-axis or not. I is either 0 or 1. So that's how you can generate this group in 2 dimensions.
Just a uniform distribution on the space of orthogonal matrices.
Yes, I know, but yeah, you're completely right. But okay.
Fancy.
Yeah, I know, but okay. But that's how it works, like explicitly in 2 dimensions. You should think of it in general like that. And it turns out that if you do that, then indeed you decouple the eigenvector structure of A and B. Namely, you can write this as a function only of the marginal spectrums of A and B. And the spectrums they are encoded by the characteristic polynomial. So there is a function that takes the characteristic polynomial of A and the characteristic polynomial of B, and that function equals that. And that function in here we're talking about multiplicative case. You can talk about additive or any polynomial if you want at some point. That function we are going to denote like that. That's the multiplicative convolution. Some function. We completely understand it. And I will say what we need from it in a second. Technically, I need to put M here, by the way, because that function depends on the size of the operators. And when you put nothing, you get the free probability version, like the actual free probability version, but I'm just going to remove that. And
So should I take it to be the definition of what you mean?
exactly,
Decouple different.
that's what I like about it. You can take it to be the definition. So if you take, so you can take it to be the definition of how, even all of that. Right, so it's a distribution such that this expression is obtained by the marginal. It's like independent, right? If you have random variables and you want to understand the joint distribution, then unless they are independent, you cannot do that. But if they are independent, there is a formula for telling the marginal with respect to the. It's a very simple formula. The marginal with respect to the marginal distribution, and that's what's happening here. So conjugating B with Q in expectation is a way of allowing you to express this joint distribution in the sense with respect to the margins.
So how general is this? So here there are two things. One, you said that the polynomial in A and B can be more complicated.
Right.
You insert randomness somehow to separate them. This is a group you are acting on one of them.
Yes, you can do
Take
that.
any polynomial, but also what about the characteristic polynomial? Can you replace it by what? What is a more general thing you can put outside so that you may expect something like that?
Right. So I think this is a good choice because you somehow want to talk about the spectrum of this operator. And so the characteristic polynomial, you can talk about the other ways of doing that, but that encodes all the information that you would care about. So I think the gameplay is about what function do you put here. And that's actually function dependent. So for the plus, you will have a different operator. And
So basically any description of the spectrum would separate like this if you have the right group.
Yes, exactly. In free probability, what really happens is that you define freeness to be essentially, you can come from different directions, but once you have the definition of freeness in place, then you can say that you understand the joint distribution of three random variables only by knowing their marginals. And it's going to give you another rule for deducing the joint distributions than the usual non-commutative setting. Here it's kind of mimicking what's happening in free probability. In free probability, what you prove is that if you have any two variables, they are kind of abstract variables, and you conjugate them by a hard unitary variable, it's not a matrix, it's just something that has certain moments and behaves in a certain way, then you get, then that will free that element from that element. And then there's a little bit exercise 5.4 in one of the books in Speicher's book, and it tells you that actually this is a way of getting freeness, and that's kind of mimicking this is an artifact of freeness, and that's what we have in finite probability. We don't have freeness, but we have things that follow from freeness. So that's really what's happening here. So we're actually, MSS, not us, mimicking what happened in free probability without having freeness.
My take is that whenever you are taking an average over a group, you are getting invariance. So you are taking average over the group, so that way the B can be replaced by any conjugate of B.
Right.
And the A can be replaced by any conjugate because of the characteristic guide.
Right.
So this means the result only depends on conjugacy class of B and conjugacy class of A.
Right, which is
In the case of symmetric matrices,
Right.
that's completely determined by the characteristic polynomial.
You're right, exactly. In case of orthogonal, then every other operator with the same, exactly.
So you can apply it in the general setting of invariant theory, anything that's invariant under some group action, you can do this.
Yeah, I can only say yes to some extent. You can replace this by any matrix that's any measure that's sufficiently random. They're called minor orthogonal in those papers. R is one example. There are many examples in which you can take many measures that satisfy certain requirement.
This type of averaging for adjoint action is used many
No, of
times.
course, but I am trying to think about
So-
many
My
very
theory is
different actions, like, I don't know, scaling
Yeah.
operator.
Right.
And whether,
Projection.
but maybe it's for later discussion, I'll let you.
But in terms of breaks, let me.
It's up to you, it's whatever you feel like.
There's a key word on this board, which is detour.
That's true.
I mean, it's not clear how this
Right.
can help you. with
Good.
permutations. Permutations are not, definitely not.
That's true. Permutation or not. And nonetheless, and that's kind of amazing, I think. So maybe let's tour back. So really what's going to happen is that we can replace this thing now. This was just a placeholder because we didn't know enough. We can replace this thing. Where is the? Doesn't. That should be enough. Yeah. We can replace the extra part that we have as if we would work with Haar measure. So let me write it like that. That's what I'm saying is that, okay, you took out the kind of trivial part. And now what's happening, you're looking at the characteristic polynomial of h squared divided by that factor that you know is there. And you did the same for the M matrix. You took out the 1 because 1 corresponds to eigenvector 1. And now you're left with these two polynomials. And what I'm saying really is that orthogonal to the all ones vector, which is the built-in structure, the permutation like projected to the perp of all ones vector behave as if, and that's amazing, as if you took a completely hard random operator.
But what exactly are you claiming? Are you claiming that this is true for any A and B, or are you using properties of H?
No, for any A and B. Right, in this case, let's go on now.
You're claiming that the detour is true not for a Haar measure, but for permutations.
Yes. But yeah, exactly. Which is unclear because like there is a big difference between completely rotating and reflecting and just flipping a couple of axes, right?
Right.
It doesn't seem as random at all. I mean, for pseudo randomness and ND factorial is a lot of randomness. And this is Aleph.
So you don't even need A and B to be permutation.
No, you don't. Yeah, exactly.
There's no error that depends on n,
Nothing.
even in 2 dimensions?
Yeah, exactly. And actually you prove it into them. So what you do is you look at these two groups, like the orthogonal group and
So you derandomize the Haar measure.
exactly. So this is what I was very thinking to say because I knew Avi would like it. So what happens is that you can think of where is the square? Oh, so let me do it here. You can think of this thing as a test function, and permutation and Haar random. These are very different, like definitely entropy-wise, very different distributions. But that test, essentially because of bilinearity of the determinant, that test is a weak test, so it doesn't tell the difference between Haar and essentially permutation orthogonal to the all ones.
The same happens at MSS, but it's simpler.
Yeah, exactly. I mean, I should stress it again. I mean, we very strictly follow what they did. We had to change almost every step, but not in a very elaborated way. Because we also always have these things that are floating around.
But sometimes having a more general thing.
Yeah, of course,
combinates,
absolutely, yeah. No,
Like the
that's
matching
why I asked
polynomial
about
not being here is actually,
Right, I think it's a good thing.
how generally,
because that seems
Right.
like such a.
Right.
precedent.
Yeah. So who can ever hope to use it again, right?
No, but this is their paper about permutations, you only have the lifting where it's just binary.
Right.
the other paper is never shown, taught, I don't know.
Right, so the first one I call pre-MSS for no good reason, just between me and I call
Yeah,
it.
what do you call pre-MSS?
Right, the one that they do the lifting, because they use the matching polynomial to understand the expected characteristic polynomial. And it's great, but in other settings it doesn't work. So in some settings it does work, but not in any general setting. And the MSS papers for me, even though the same MSS, I like the fact that they use and develop finite free probability to understand this. So that's for me is the MSS papers, and the pre-MSS is another paper. But they developed the interlacing. So time-wise, by the way, I mean, there is a natural place to stop in 10 minutes, but I'm not
Yeah,
sure.
let's,
Yeah, it doesn't matter, it's up to you.
you don't even need a break if you don't want.
I don't need a break, but I don't know. People maybe want to.
So if you think in 10 minutes, that's good.
Okay, so serious. So let's continue there. So, but okay, a word about the proof here is what you do is you look at the generators of the orthogonal group and of the essentially permutation group, but you need to work orthogonal to the all ones matrix. So you look at the simplex essentially, as you project.
But it's enough to prove it in two dimensions.
Exactly, it's enough for two dimension, and when things go over season.
Because they generate, all the.
Right. Yeah. And to do that, you kind of remarkably prove actually invariant result, but something stronger than that, and from that it follows. But yeah. And going back to the involution case, so I don't know how to prove that. So if you replace, and I would like to know what can be said, but if you switch P from permutation to involution, then even at the generator level, it's not, I mean, the invariant claim doesn't work. Maybe it's still true, but the engine below the
Mathematically, it doesn't make sense. I mean, you're taking some arbitrary subset, the involutions. You conjugate only with a subset of the whole group. Conjugation usually.
Right, it's not a
subset.
Yeah, that's true.
I don't see why it would be true.
I mean, you should replace P by an evolution. You should replace P transpose MP by an evolution.
Oh, that's it, the evolution.
Right, exactly.
Yeah.
Okay, so that's fair.
Yeah, I mean,
Okay, good. So, but I would have hoped to have a simpler P here, not just a permutation.
yeah, but that's not the same model. But what I didn't understand is why you didn't from the very beginning just take P transpose MP to be a
To
random.
be something, right? Yeah. So the reason is because I wanted to.
Same thing, right?
Yeah, but the reason I want to think of this P as kind of something that decouples H squared from M. So if I would have called it.
It would be natural to take a subgroup, like
Right.
the cyclic group.
Right, but not evolution.
certainly not the subset.
Yeah, that's true. But okay, yeah. Wishfully, I would have liked that because some reasons. I understand. So just to recap, we just said that lambda2 of this thing is lambda2. So I understood the expected characteristic. So going back to lambda2, we want to figure out what is lambda2 of this thing. I just told you that one root is c squared, and it's kind of obvious, but you should also trust me that c squared is going to be the largest root of this thing. I mean, I didn't even tell you this is real-rooted, but assuming it's real-rooted, c squared is going to be the largest root. So we really want to understand the max root of this thing in order to get the second largest root, the expected characteristic. So the question is, what can I say about the max root of this thing? Right, that's where we're at now. We want to understand the max root of this polynomial, and I told you nothing about this operator, so I'm going to tell you exactly what we need, but that's the question. Maybe we should go here. So the max root function, even though in the picture I just erased, is actually not that terrible. I mean, in convex combinations of polynomials, it's monotone. You can have some nice things to say about it, but it's a number, right? Given a polynomial, it's just a number. You can play with it. You can do complex analysis of this thing. It's just a number. So what you want to do is to have a kind of a mechanism that will also encode the max root, but you can play with it. And that's called the N transform. I think I need to go one step further. So I wouldn't call it a detour, but just kind of a reminder. So I'm going to define what's called the N transform and then tell you what you need to know about this. So we know what is the Cauchy transform, right? I wrote it somewhere there. We will actually need a slight variant of that, which is called the M transform, moment transform, even though the Cauchy transform already puts the moment. So we just, dry definition. In a sense, it's the kind of the wrong definition, the right definition is this, but whatever. This is what it is. And if you think about it for a second, it's going to be 1 over D, very much like the Cauchy transform, but you're going to have this lambda I sitting on top here. And because you multiply by X and that's one, that's what you get. And okay, so I'm going to assume lambda 1 is a positive, it's going to be positive in our case. And we don't know if, just so that I multiply. So once lambda 1, it's so the max root of this thing. So once lambda 1 is large, is positive, the picture of this thing is as follows. So this is lambda 1, the largest root of the characteristic polynomial. This is lambda 2 and so forth. And right, it looks something like this. And then you have a bunch of more of those and one like that. But this is how these things look like. Right? To the right of lambda 1, you get something that looks like 1 over x. It looks like this. And what I want to define is essentially a max inverse of this function. So you can invert this function because it's not invertible, it's not monotone or something, but you can invert it if you restrict it to the right branch. So what I'm saying is that, restricted to lambda 1 onwards, the M function, okay, is strictly monotone decreasing, so you can invert it, and we're going to denote the inverse of that by this fancy N transform. I'm going to use Y because it's an inverse of next. So N of Y is going to be, well, it's a function. So it's a function, well, let's first do the type. It gets any number between 0 to infinity, right? Because every value between 0 and to infinity is getting there, a Y value. And it produces a value in lambda 1 infinity. And that's just is the inverse of M restricted to lambda 1. Maybe I overcomplicated it. But I'm just trying to invert M, the N transform. For there is a reason why I chose this particular transform. You'll see in a second. I invert it to the rightmost branch. And this is the function that I like because it encodes lambda 1, right? Because if you plug values of y that are closer and closer to infinity, right? So if I get a value which is quite large, I get something, this is the N transform. I get something which is getting closer and closer to lambda 1. So it encodes lambda 1, but it's a function, you can work with it. You can do things to it. It's essentially a softmax, but a very well chosen softmax. And why do we like the N transform? Because of the following theorem that I'm going to state now. I have to admit, I saw Ramon's talk yesterday because I wanted to, and you make it seem so easy to move these things. 3 times a week at the gym, and I can't pull this off. So, okay. So here is a theorem which mimics a theorem from free probability, but it's a completely different proof given by MSS, and it tells you, and that's the only thing you need to know about this multiplicative convolution for the purpose of this talk. It tells you that if you have any 2 polynomials, essentially, then you can bound the N transform, which is again is a machinery for getting bound on the max roots, right? essentially by the n transform of the individual polynomials. Just point-wise product. That's amazing. I mean, that would be amazing as well because you can easily calculate the thing. Now there is a little bit of a technicality here, but it's only because I didn't normalize it correctly. So there is also this factor sitting here. But it's not a real thing. I mean, this is this is 1 over the n transform of the identity matrix. So if I would have multiplied this, put one more copy of this here and here, then you get the right normalized version of the n transform. It's called the S transform, but I don't want to write another transform. So I'm just going to write it like that.
So should we think about this inequality as becoming equality as m goes to infinity?
Exactly, yeah. So good, thanks. So in free probability theory, this is an equality actually. And kind of remarkably, you don't pay by working with finite operators, you gain by working with finite operators. Maybe much like Amand-Bopana can be, you can get better than Ramanujan graphs in a sense. But it's not quite related actually. So this is a theorem. It's a very non-trivial theorem to have. So let's plug in what we have. I mean, MSS proved that, and also in free probability, you need, some positivity from this polynomial. You need the roots to be positive. In MSS, this operator here that we have, it has like half ones, half minuses, minus one. So you can't really apply it immediately. So you need to generalize a little bit, and you do that, and everything's fine. In free probability, you need one of them to be positive, and one of them can be maybe anything, or maybe something more relaxed.
I feel like I'm
Sorry,
I'm slowly losing you. I understand that you're trying to decouple two things that shouldn't be decoupled, so you need to work hard. But then you start to give us these weird transforms
Right.
with no justification.
Right. So let me just recap for a second. So we agreed that we want to bound the max root of this thing. Because the max root of this thing will be actually the bound on the second largest root of the expected characteristic power,
Right.
and then interlacing will do the thing, what we need. But we do want to bound the max root of this thing. Now, this is a max root of some, two polynomials, and there is an operation of them I told you nothing about, actually. And now what I'm saying is that I don't know much about the max root of this thing. I mean, not directly. What I know is how the n transform of the multiplicative convolution of two polynomials behave. And so that's the story here. And the n transform can be used to get a bound on the max root, because no matter what value it fixed to the n transform, it will give you something larger by definition than the
Right.
max.
We have here two things, the multiplicative convolution, which we haven't defined,
Right.
the n transform, both, I guess, are coming from free probability
Yes.
theory.
It's just like if you have the ordinary convolution, Fourier transform just becomes a product.
Right,
So the n transform is exactly the same thing.
Right.
It's not a
makes you
convolution.
get a
At
product.
least in the infinite dimensional setting, right? If you take the multiplicative free convolution, you take this n transform, it just becomes the product of the n transform.
So
So
we
the
can
logic
think
confusion.
of the n transform as some kind of Fourier
transform.
transform.
Exactly.
In this non-Fourier
Dimensional,
exactly.
Exactly. Just the Cauchy transform is the right thing and not the Fourier in this case. Right.
Okay.
Why it's that formula?
Yeah, that depends on free probability. Like,
Okay,
You didn't define the multiplicative.
right. Yeah, I didn't.
Nothing to say.
So I want to say one more, but
So the trivial one would be the sum of the maximum? That's the old zigzag?
that's obvious. Yeah, right. The max root. Oh, I don't know. Oh, good. That's a good question. I don't know if from here, if you cash out using the trivial bound, you get RVW. I'm not sure. Probably.
You want this to be a function of the maximum of this and the maximum of this. But that's what you're gonna get there, or?
So we'll see what we get. But actually, it's a good question. Whether if you cash out with the trivial bound here, you'll get something that we know. That's very interesting. I don't know. I didn't think about it until you said that. Should have, but I didn't.
what's the trivial bound?
The bound on the max root is the maximum of the max root of the individual polynomials. Yeah, but good. I don't know. Interesting. I don't know. No way. Because right. Sorry, you don't have G anymore here. This is one of them is just M. See, so you don't get. Right. But maybe you get something about H. I want to say one thing that I forgot about. Oh yeah, maybe I should say that. Ramon, correct me if I'm wrong, but what's nice about free probability that we learn classical probability in the second year or something, or first year, and no one tells us that there are more probability theories. Namely, particular, there are more notions of independence in the sense that if you have that notion of independence, you can compute joint distribution from the marginals. And it turns out there is exactly one more. So there is the one that we know, and there's free probability. There is another weird one, but free probability. And it's axiomatically, you can prove that there are like two probability theories. There are only two courses you can take. And in terms of generating functions, or transform, one works better with the Fourier transform, and the other works better with the Cauchy transform. And somehow this is what Amon said is what I should have said. This is right. You do the right transform, the correct transform for this probability theory in this world, and you get this with the quadrant.
An analogous central limit theorem.
Yeah.
Probability.
Yes, and so it turns out that the Gaussian distribution, normal distribution, is the semicircular element.
So it comes out to be Gaussian anyway.
No, semicircular.
Semicircular,
Right.
yeah. So,
Yeah. And a very strong, and weird things happen in probability. So there is more relations between semicircular and Poisson distribution, and so forth. Square root of one of the other. Yeah, it's a really enlightening work to see, I think. But down to earth, let's just continue this little calculation just a little bit more. Because now let's make sure if you want to bound the max root of this thing, it's enough to understand or to bound at least the n transform of this thing. So P and Q are going to be these polynomials that are written there, chi of h squared over x minus c squared and the other. And we can actually compute the n transform of m, not of h squared, but we want it to be a function of h, so that's fine. So what will happen is that let's plug in, let's look at n of, now technically I should write this thing for P and that thing for Q. You should trust me that you can actually ignore that and put this thing instead, and that's only work against you. It makes things simpler. So I can write the n transform of the characteristic polynomial of h squared, which I'm just going to write it h squared, because I'm lazy. So maybe, sorry. Let me write it here. And I actually planned on developing this, but I do want to talk about the other bound. So this you can show easily, just a calculation. You completely understand M. This is the square root of y plus 1 over y. Just a calculation that you do. So it takes a square root of this out. And then you have a bound.
I'm slightly confused because here it is important that lambda 1 is the largest root, right?
Yes.
If you replace it with h, then c squared is the largest root.
Right, but
Then what do you get out of n?
You're saying that you're confused about me removing that thing. Yeah, right. You need to massage it a little bit. You're right. I mean, you can't just ignore that. That's the largest root. So what I'm saying is that essentially you can ignore that. Okay, well, anyhow, I'm not going to go into calculation, but you can safely ignore that.
Okay.
Yeah, you're right. I mean, in order to say what I need to say, I have to elaborate a bit. And then, just calculation.
Just from the very beginning, restricted all of these matrices to your orthogonal complement of the R1's vectors. Right now, they're n minus 1 by n minus 1.
Right.
Nd minus 1.
Right, so it doesn't really, yeah.
And then you don't have to divide by anything.
That's true. Yeah, just to relate it to the D2 like in a vanilla way, but you're right. Yeah. But anyhow, from here, it's just a calculation that I wanted to do, but I think it's maybe, so you just compute this, so you get a bound here, and then the max root, that's maybe the fun element for this, the max root of the polynomial that we care about. Let's call this polynomial C for care about. Of Cx. Maybe C, not getting the variables placed. You can, I mean, it's always bounded from above for any y, right? So you can minimize over y larger than 0, y divided by 1 plus 1 square root times the n times of h squared y. Sorry for the little bit of mess here. And now you get this minimization problem, which you translate to the minimization problem that I told you about. You move from y to x. Essentially, that's it. One more board of, like small board of calculation, you get the ZH function that I was talking about. So I think that's all I want to say. I mean, that's all I have time to say about the upper bound. We can talk about the lower bound now, or we can take a break, but I'd be happy to just proceed if everyone's all fine with that.
The prerogative of the speaker, or
Always,
if you are happy to proceed, then you proceed.
Okay. I'm trying to.
So just a quick question.
Let's take a
Hey,
5 minutes? Let's do a 5 minute break, and then I can also maybe we can. Sure. So let's do a 5 minute break.
5 minutes,
Yeah,
right?
so thanks.
So 5 to 12, I guess.
Okay. Yeah, sorry.
It seems to suggest that the picture you drew, that the bound should be best when y is very large.
That's true, but you see, there is this factor. That's a great question. So when y is very large, you see, I mean, you want this thing to be small. When y is very large, you get better bounds, but this thing goes to 1 when y is very large, whereas where it's not too large, it goes to 0. When it goes to 0, it goes to 0. And so the sweet point is somewhere in the middle. Right, so it's not really a normalization. The right way to look at it, it doesn't make sense to look at a small one. When you normalize it correctly, you see that it always looks something like this. So there's always something there. This is lambda 1. There's always the bound is always somewhere in the middle. And that middle depends on the entire spectrum.
Also, these functions are only. They are. I see.
Yeah. I have an example, but
Why do we move from non-matrix operators to the word probability?
with the free probability thing.
No, why does
Oh,
two different probability theories have to do with
Right.
this operator? And commutative.
right, exactly. So yeah, so in probability theory, you always work with random variables which are non-commutative. That's kind of by definition from the beginning. If you work with non-commutative random variables, then free probability is, I would say, a good choice, but that's the only other choice. So good thing it exists. It gives you a way of talking about really the eigenvalues of matrices. So that's how it became.
Really, it's about operators and their eigenvalues.
Exactly.
Word probability,
No, there is
is it
a
useful as an intuition? Is it useful?
right.
You know how we think of probability? right?
Yeah, I know.
Question.
I understand, yeah, and some people say that free probability is really algebra, not probability.
So that's what I said.
Right, that's not, yeah, that's, you're in a good company. Many people think of like that, but you do include moments of something.
Of some elements in some algebra.
Right, so for example, for matrices, the way to encode moments is like if you have a matrix A with eigenvalues lambda 1, lambda n, then the nth moment will be the trace of a, will be normalized, but the trace, this is the kth moment, for example. So you can think of the distribution in which you sample an eigenvalue uniformly at random, and then it is a probability in that sense. And then you ask, if I add two matrices, what can I say about the eigenvalues, this eigenvalue distribution of the sum? So you can say nothing, it depends on the eigenvector structure, but if it's unrelated enough, then you can say so. But there is no probability, I mean, there is some Lebesgue measure going on there, but it's not probability per se. It's like
If you pick two matrices like Gaussian,
yeah,
random,
right.
and you add them, then this bound will be
Right. By the way, Gaussian, for example, if they're large enough, they approach the semicircular.
yeah.
Right. So that was only
That's why I
before.
asked, yeah.
Yeah, of course. Yeah.
But then the moments of the sum are the
Right. So I think initially it was,
normalized sum of the moments.
yes,
Like when you had Gaussian,
Right,
normalized
exactly.
by them, yeah.
exactly. And also there is a very nice underlying combinatorics around this. So it turns out that probability theory in general, you can prove, for example, the central limit theorem. You don't usually do it like that, but you can prove the central limit theorem using permutations, partitions in a sense, on schematic set. And here, non-crossing partitions will come into play. Turns out that's kind of the underlying combinatorial difference between the two. That reflects on the choice of the Fourier transform versus the Cauchy transform.
But I don't know, and I wonder if this extended to general invariant theory, and you take the invariant.
Yes, that's true.
I mean, the
happens?
eigenvalues are invariant under conjugation.
Right.
Okay, so that here the spectrum is a collection of invariants, but the general group of functions have their invariants.
So maybe Ramon,
Ramon,
do you know? I don't know.
free probability generalizes to invariant theory.
Free probability is the infinite dimensional limit of what he's talking about.
No, he's talking about linear operator.
He's talking about finite free probability.
No, but he's talking only about a particular group action, namely the action of unitary or orthogonal groups
That's
on
not free probability.
operators.
That's not free probability. That's something that exists for finite dimensions. Free probability is the asymptotic limit of
That's
dimensions.
not what I'm asking. Whether it's finite or finite dimension or infinite dimension. Well, the invariants is a spectrum, and this is the invariant under conjugation by whatever. So there is a group action acting on object, right? Which in particular, here is a particular case, but you know, a zillion of group actions acting on objects, and they're different invariants. It's not a spectrum. I mean, in physical dynamical systems, energy and momentum are invariant, right, of certain action. And does this extend to settings of system? I mean, invariance theory is full of group actions and invariance for the group actions. And I wonder
what are you trying to prove?
Can you separate?
I want the same. I want exactly the same.
This is not, has nothing to do with free probability, what he wrote. This is a finite dimensional computation. This is what he calls finite free probability.
Yeah.
That's something else. That's not free probability. Free
No,
probability.
I'm talking about the formula, the separation of using this formula. There's a formula that separates the D2. This D2 is free probability, right?
No. This is what he calls finite free probability.
Well, if the operators are infinite dimensional, it's not free probability.
You don't have a group anymore.
If you put an N over there.
So all of these objects have the same infinite dimensional limit.
Yeah.
Right?
There's
So
no infinite group acting on the infinite objects.
But it's not compact. It's not.
so
So there's
It's
no
not
measure.
compact.
no,
But
but these are open questions. You know, for example, if you start not with the free group but with the surface group, and we want to construct finite dimensional random matrices that converge to them, you know, these are that's not the frontier. We don't know this.
you don't know. Okay, so there
This
are.
is kind of at the frontier.
So there's a hyperbolic thing that
When it comes to invariant theory, I can give you a different answer. Because invariant theory is things closely related to it that we use all the time to do computations with random matrices from groups. And it's called Weinberg calculus, and we use it like bread and butter.
I want to stay away from matrices. I want to think of completely different, group actions on whatever surfaces. But let's continue.
We would like to start from a discrete infinite group and then find random matrix models of them.
Let's hear about the roadmap.
Actually, can I ask?
yes.
Kind of a orthogonal question. I'm not familiar at all with free probability. But like for me, this looks very familiar, just like, from Fourier transform.
Yeah.
Right? I mean, this is,
It is.
I'm ignoring for a second the symbol of the characteristic polynomial. But right, this is basically like the definition of some kind of convolution.
Yeah, that's exactly true. But that's the right transform for this setting.
Sure,
Yeah.
like
Exactly, you're
probably you have to find
Right.
the right transform where you
Yes.
can do Fourier analysis again with these.
Exactly.
So like
So you ask,
really,
where's the group?
what?
So yes.
Yeah, okay. I mean, Fourier transform is you need some kind of group. So like what's going on here if I understand, is like you can almost take this as your sort of definition of
Yeah.
convolution, and then
You can, yeah.
you kind of.
It was actually the way they define it in the first paper.
Oh.
Yeah.
Okay.
And when they figure out that these were known, and they have explicit formulas, like back in the 40s, they didn't need the formula, but
Okay.
of the coefficients and so forth. Turns out that people actually try to prove the Riemann hypothesis using these things like real-world polynomials. And at that point, because you can just go to the axis like that. There is a mature theory about that, much more than what I'm saying here.
Yeah.
Right, so in a sense, it's more related to that than to free probability in a sense. But yeah, I can't say much more. Maybe offline. So let's do the lower bound now, right? The lower bound now, right? Completely different. Actually, it was okay. I mean, obviously, because you get the same bound, it's not unrelated. But for us, it was unrelated at the time, and actually, even now, I'm not sure I completely understand. I feel like we should have gotten to that function, you know, in one shot, not going with two different theories to get there. But I don't know. So lower bound. So what we want to prove now is that, right? So for every h, right. So nice.
Every,
Sorry.
for every p that exists.
Right. So what I prove is for every. Let me just phrase like that. So for every nice, the upper bound didn't need any niceness property. Math doesn't also need nice property, but we did because it's easier, you'll see. So for every nice h, nice is a very simple thing. I can tell you what it is, which is vertex transitive. Nice is simple. We can completely characterize the non-nice graphs. It's a union of 4 cycles and matching. So it's very easy, so you can ignore that. But the laziness part is the transitive, vertex transitive graph. Again, every time that you see an H, it's on D vertices and it's irregular. And for every n larger than 1, there exists a graph G, maybe we should call it G sub n, so that we'll remember that it is on n vertices. It's going to be D regular. And such that the bound that we proved to be an upper bound is also a lower bound. So omega, now omega, not lambda, not omega from yesterday. Lambda is or at least minimum that we have. And there is a little of one reduced because we use the trace method in the trivial way. Okay, this goes down, vanishes as n goes to infinity.
So,
Lambda 2.
silly question.
Yes.
What happens if G is just disconnected,
No, no.
even with the trivial?
Good, so that's a good point. Even if G is disconnected, and even if none of them is an expander, none of them are expander, maybe H is a cycle, still you get a good bound, or some bound. And it's not necessary, I mean, we used to think, I should have said it this day, we used to think that only when G and H are good expanders, then you get a good expander. But actually, it's not the case. The labeling gives you enough randomness so that even if G and H weren't good expanders, you can get a good expander.
G is basically a random graph, right? Randomize the labeling.
Yeah, only H, my bad. Yeah. So you choose the labeling, right? Right, so for,
Shouldn't the lower bound be for all graphs? I don't understand. For the upper bound, you show there exists a graph. So for the lower bound, you show for all graphs, it's lower bounded.
oh my god, yeah, sorry, this. Yeah, thanks. I got confused here. Sorry, for every
You want
H,
to start for every graph.
right, and for every G. Sorry, my bad. Yeah, of course.
No.
It would have been enough to show that for every graph there exists.
Yeah, of course. No.
It's the stronger one, yeah.
Right, that's what you want. Yeah, sorry, my bad. No matter what G and H you take, Zig-Zag has a limitation because of the structure of the Zig-Zag. But the nice thing is that the same limitation that you can actually match.
So just for all G and for all labelings of G.
Yes, actually it is right. So it's the best labeling would give you anything. I mean, yeah, for any pi gen pi actually. if you want. Because the zigzag is defined actually with respect to the labelings. No matter what labelings you take, you won't be able to get them below that. Okay, thanks, sorry. So you have it 20 minutes or 15?
Yeah, we do have.
That's right.
20 is good. 20 is not good.
12:30 we go.
Great.
It's the maximum between.
So, okay, so the starting point is not so surprising. We just use the trace method in a simple way. So, like you want to bound lambda 2 from below. So maybe lambda from below. So let me write it like that so that you will see it better. So I guess we all kind of know, I can say how, but you can bound this using the trace method, right? Because the trace of the power of a matrix encodes the number of closed walks there or cycles there. But you can essentially write it like that. And you can bound it as the number of k, let me call it cycles, even though closed walks is a better name. Just used to it. K cycles in the graph that you care about. To the power 1 over k minus little of 1 for some k. Like you can choose a k for which this holds. The little of 1 requires k to be like log n or something for constant degree graphs. But let me do it like that. There exists a k for which this holds. So the problem really is about counting k cycles in the graph that you care about. And that's difficult because we don't really kind of get g. We don't know what g is. And so the way around it, and it's kind of always a bit surprising that it works, is to kind of kill all the non-trivial cycles in G and just replace it by a cover, or in this case, the dRA infinite tree. So it would be enough to replace G with TD, the infinite dRA tree, zigzagged with H. And you can imagine what that is, right? What you do is you zigzag to the infinite tree. It's a local operation. It doesn't care the graph is infinite. And actually what we always do in this case is we also truncate the tree a little bit. I will say more about it, but we just remove some of the edges so that we'll be able to count something in a recursive way. And removing edges, this is a shorthand for we removed some edges. Trust me, we don't care about what these edges are. It can only reduce the number of cycles. So that's what we need to do. And if we are going to call this thing C sub k, then what you usually do is you, like in the standard case, you just compute ck. It's related to the Catalan numbers and so forth. But in our case, you have this weird graph, so we are not going to be able, it depends on h, we're not going to be able to actually compute ck, but we are going to be able to approximate it. And in order to do that, let me start first by defining the generating function corresponding to it.
Say here k cycles or closed walks and so on, like you mean from a specific vertex?
Yeah, sorry, right, good. Because here you are infinitely many. So,
Why is this?
right, starting originate at sum v. And here I'll call it from sum r for root. Sorry, my bad, yes.
And the vertex transitivity says you don't.
Right, you don't mind, exactly. That would be helpful for us now, exactly. Usually you don't care who anyhow, but for our case, it will be more. Right. Thanks. So CZ is going to be the just generating function of this thing. And what we want to get is we want to understand CZ at least approximately. So far we kind of did nothing. In the simple settings where you can actually, the graph is simple enough, you can really compute CK. You don't go and talk about the generating function. But in our case, it's going to be sort of the only way forward, I think.
So for the cycle, it's obvious.
For when H is
H
cycle?
being a cycle.
Oh, good. Yeah. And you can make a recursive relation with respect to the cycle length.
Yeah.
Right, good, yeah.
In generating.
Yeah, right. That's true, actually. So you really can't, but you don't need like do complex analysis.
You couldn't now really use free probability. Just take Z, the group Z2, take a standard generator, free product with the matrix algebra, and then just compute the spectral radius of this, which presumably would give you the same formula just by entering.
Yeah, I think that's the way to connect the two. You're right.
It should basically be the same.
Yeah, I know, and it gives the same answer, so I cannot say no. But let me just continue. And yeah, I agree. I mean, I'll be happy to talk about it because it feels like we're doing the same thing.
I mean, the way you prove this thing is through generating functions.
Right. Right.
Probably just mimic
The same thing. Yeah, exactly. But
the
you.
whole machinery there already.
Uh,
You're already using in the upper bounds.
yes, but you see, this is I don't know. Okay, maybe yeah, because it is free probability now, not finite free probability.
Yes.
Okay. Yeah. Good. Okay. So, but I'm still going to continue the way I plan. And it will be interesting to contrast that. So we want to figure out what S is, but it will be easier to count like simple case cycles. Namely cycles that start at the root and visit it twice, at the beginning and at the end. Okay, so S of Z is going to be, the generating function where Sk counts the number of kind of simple visit twice. Technically also no empty, but okay, at this point, simple case cycles in the graph that we care about. Again, originate at the and it's enough to do that because what is a cycle? It's a sequence of simple cycles. So in terms of generating functions, you'll get the recurrence, you get the relation. Looks like this. Intuitively here, I think. And so once you understand S of Z, you can understand C of Z.
Why is this easy?
Right, that's no, that's good. Yeah, it's so let me.
No, it's
The
clear.
power-
I know.
The power.
Right, no, I know you know that, but really just count the number of cycles, the number of 2 cycles, and so forth. And there is some technicalities once you move to complex analysis, not just generating functions. There is a question of the convergence convergence. But and I'm sliding through, but you're right, it's not right. Okay. And now the cool thing, and I wonder, Ramon, how it's related to probability. We are now going to use a strong big hammer from analytic combinatorics. And I wonder what's kind of the analog with probability there. So it turns out that, in order to understand the S of Z and C of Z, we are going to prove that S of Z satisfies a certain functional equation. So we're going to write it down. And then there is the theorem that will tell you that if you understand the functional equation, you understand the coefficients of its solution. So let me be a bit more slow. So the proposition that we prove, and that requires some combinatorics. So that's why I did wonder how we can do it with probability, which doesn't do that. Is that maybe I'll write the proposition upstairs. We need a bit more room. So the proposition is so S of Z satisfies the following functional equation. And so let me write it, let's just plug it in. S of Z equals Z squared times A sub H of S of Z. And I should define that, but 1 second. So you see S of Z is a solution to this, in power series, in the ring of power series, to this functional equation. And the hard part is to kind of find the functional equation combinatorially. So we need to find A of H. It was kind of quite difficult for the Zig-Zag and much easier for the derandomized doing. So let me tell you what it is, but not prove that for you, okay? So what is A of H? So what you do is you look at H squared, which we knew will make an appearance. And what is A squared, right? You have for every 2 nodes, for every length 2 paths between them, you add an edge. But here you kind of remove. So maybe let me define H tilde. you take H squared and you don't count the length to path that goes through some fixed V, a light V. So you fix a V, because the graph is vertex transitive, you don't care who V it is, that's the real point where it's difficult to do it otherwise. And you just look at A squared and remove that little V, all the paths that goes through V like that. Why? Well, it's like, boils down to looking at the zigzag product and trying to actually truncate the tree in a certain way so that this will hold. It's like a blanket that you move around until you can find this function. Oh, sorry.
השמיכה קצת.
Blanket, yeah.
I understand about the blankets, I didn't understand the rest.
Oh, is it? No, I'm saying I hit this. Maybe I shouldn't say, but I hit this till the certain truncation that we are doing.
So there's an infinite tree, are you truncating to make it finite?
No,
No.
I'm just truncating it so that I can make a functional equation. I want this.
It's too much to go.
It's maybe but maybe if we have 5 minutes, I can do the easy case, the usual case, and then you can see. But then now you look at this thing, and then A of H of Z is the power series that counts the number of K walks from a neighbor of V to a neighbor of V in this graph. So number of K paths, it's not a cycle, K paths from a neighbor of V to maybe potentially some other neighbor of V in this weird kind of graph that appeared here.
Doesn't seem to simplify much. I mean, if you give a functional equation for an object by putting a function that's a very similar object.
Right, but you would hope to kind of have a cleaner version of this thing, right? Like, why you look at this thing and
Ask
Why this particular functional equation helps any? Because the object defining the functional equation is of the same nature as the solution.
no, that's true. So that's fine. You say that's a positive thing, I guess.
So do you ask for some sort of periodicity on the labeling of the infinite tree?
Because of the vertex
probably you want to
transitivity,
think about it
right.
as a covering of the other one, so that comes with
a certain
periodicity of the labeling, right? So I
But it
think
doesn't matter.
it shouldn't. I mean, because of the vector transitivity, it doesn't matter.
maybe the functional equation, I can imagine that you want to say that your MK is large enough, you are getting kind of the same number of cycle. The reason probably is because of this periodicity of the labeling. I mean, if you kind of put it in an irrational labeling, then I don't see why you should have the same pattern.
Right. This is with respect to a fixed labeling of TD. Yes, but I'm not sure about.
I have to think about this.
Okay. Sorry to do it, but maybe offline so that we can. Yeah. Okay. So anyhow, you want to understand the generating function. You maybe massage it a little bit, but then you can show. Generally, you can show maybe that it satisfies a functional equation, and then what? And here comes the big hammer, which again, I'm curious about the free probability, or how does it kind of bypass everything? So, I'm noticing that I'm trying to avoid moving the boards. So here's the big hammer theorem. I don't know what's the name of this theorem. But it tells you the following. It tells, say you have this function zeta of z, and it satisfies, this is our S in our case, but usually it's not like that. Zeta of z equals z times p of zeta of z. Okay, so very similar to what we have. We have a square there, don't worry about that, but you don't need this, you want something outside there. And assume that phi is nice. So if P is nice, and by nice, I mostly mean analytic at 0. There are some other requirements. The Taylor expansion around 0 should have positive coefficients or non-negative, which is really weird in general, but in combinatorics, it's what we always have. It's a generating function that counts something. There are like 3 more weird requirements. The 3 weird requirements actually give you the characterization for which the graph that don't work. And it's hard to figure out what graphs don't work. And somehow you get it spitted out from this theorem. So if phi is nice, and again, you want to understand the nth coefficient, like the coefficient of z to the n in this function, then you can actually do that. Then it turns out that the nth coefficient, let me write it like that, the coefficient of z to the n, so in the function that you care about, it turns out it is going to, I mean, if something, it should come from phi, and it turns out that you should differentiate phi, plug tau to it, and it's close to, and take it to the n, where tau is a solution to the characteristic equation. It turns out it's the unique solution to this equation. So tau is the solution, sorry, is the solution to this thing. Turned out it's unique. It is nice.
Tilde mean over the equal?
Sorry?
What does the tilde mean above the equal?
Right, so asymptotically, it's 1 plus literal of 1 if you take the nth root. So if you take the nth root, which is what you
Nth root of the coefficient of z to the n. The nth root of the coefficient of z to the n converges as n goes to infinity to phi prime of tau.
Exactly. And you can, depending on phi, you can get better and better approximations, but for us, that's enough. We anyhow lose in the trace method, so. So that's a kind of I don't know what to make of it. It's not trivial to prove, and it's I'm not sure how it relates to free probability. Somehow both of them go through the Lagrange inversion formula, but other than that, I don't know how to say much. And it turns out that if you take our A of h, we can actually also show that this A of h is like, we can kind of understand it in terms of the Cauchy transform of h squared, doesn't really matter. So it turns out that our A of h, if you apply to that function, you get the result. I'm not going to do that. Instead, what I plan to do is to actually get you in like 5 minutes the 2 square root of d minus 1 bound using that theorem. Just instead of cashing out, exactly, because it's not fun to find the derivative of this and work it out on the board. And it's not very nice always, so you have to have some constraints on h that will come up. And so what I'm, just to recap, what we're using is this theorem in order to understand S of z and therefore C of z, and that's it. But I think it's really kind of nice to see how this theorem spits out the 2 to the square root of d minus 1 bound immediately. You don't have to use this theorem, it's easy enough to just calculate, but it's nice to see it in a simple case. So maybe let's just do that and then we'll finish. So again, we are like back to this is I shouldn't write why, because every person has its own version of understanding why 2 square root minus 1 is the right thing. It's the spectral radius of the infinite tree, of course, and so forth, but I really like to see it coming out of this thing. So let's look again at, let's try to bound lambda of g without zigzagging anything, just find out lambda of g. And so
Gil, could you say, why does this control the second eigenvalue and not the first one? That's a basic question.
No, it's a good question. Because the all one's eigenvector is not an it's not L square integrable. It doesn't exist in infinite operators.
Oh, okay.
I know, but it's something I should say. You look at some Hilbert space and then it goes. Right, so everyone says that these are the trivial eigenvalue, but the fact that it's there means the graph is finite. So I think it's a bit of information. You're looking at a finite operator. Yeah, but yeah, I skipped that part. You're right.
Are you talking about 2 square root d minus 1 now?
Good, yeah, so I felt like I'm doing a job. So instead of applying this theorem to our setting, which will take me too much time and it's not really interesting to look at, someone doing at the board, I just want to use this theorem to get the 2 square root of d minus 1 bound.
Along Mopana, you're proving.
Along Mopana using this.
Yeah.
Right. So you don't have to use this.
Yeah, there is no H.
Right. But it will show you the truncation and something nice about the symbolic method. And so I think it's a very nice 5 minutes, like going down back like that. kind of things you know. So, and I really like this proof. So here's the proof. So you look at the infinite DRE regular tree. So this is the root, maybe. And what I'm going to do is I'm going to truncate it like that. I'm going to remove one edge. That's the tilde in that case. In our case, the tilde is kind of different. And now here is informal instantiation of what's called the symbolic method, which you can make formal. I don't know if many people know about it, but it's a really nice method to work with generating functions. So I'm going to write things that looks like someone should formalize them, but they are formalized. So what is a cycle? Without defining what C is, it's not a generating function, just C. So what is a cycle in this that originated the root in this thing? So to specify a cycle, you need to tell me to which of the d-1 neighbor that you're left with you went to. And I think this is related to your question about how the labeling happens. But no matter how it happened, you have d-1 options to tell me what the cycle, how the cycle starts, unless it's finite, but unless it's empty, but how the cycle started. So I'm going to write like symbols without really. And then you need to tell me, you know, maybe you're here. You need to tell me what cycle did you make before you reach back to R. And that's why I did this truncation, because now it's kind of the same construction, right? If I'm not allowing you to go back to R, it's kind of truncated.
You're counting simple cycles.
Simple cycles, yes, and right, and not going up. Right. So you need to tell me your cycle, and then you can go up, and then you can repeat this as many times as you want. So you take a sequence of those. Right, so this is like a caveman version of writing cycle. It's not formal, but like, you understand what I'm saying, right? You have d-1 options, each of them is a step, and then you like hang a cycle here, as many cycles as you want, you go up, and then maybe you do it again, and again, and again. And the empty cycles is also take care of the sequence. And then, even though this is kind of informal, from here you can read off the generating function, or at least a functional equation for the generating function. Because you can say, well, C of Z, now this is actually a generating function, this is like, nothing like this. But C of Z, well, what is the sequence? I mean, you try to say, let's go with this, it's 1 minus 1 over, not worry about anything. And then you have d-1 options. I'm just going to multiply d-1 times. Each of them is a step, so I kind of need to encode the fact that I did a step, like multiply by z to shift it to the next part. Then there is a C of Z, and then there is another factor of Z that comes from going up. So do like that. So you got this functional, you got this equation, you can actually solve it. It's a quadratic equation, you can solve it and get what you want, but let's not solve it because sometimes it's too hard to solve. Let's use this theorem instead of actually solving for C of Z. So the first thing to note is that really C depends on Z squared only. You can also see it from here, but also combinatorial, you have to go up and down. So you can write C of Z as some other function in Z squared, an even function. And then you can write this as D of Z, let me replace Z squared with Z in one shot, equals to 1 over 1 minus D minus 1 Z D of Z. Right, it's a Z squared, but everything is squared, so I'm replacing it with a Z. And if I want to use this theorem, I really want to have a Z here. I'm just going to add it up. And now I'm fine, because now if I'm called this E of Z, it's nothing, it's just shifting things by 1. It won't affect the asymptotics of anything. Then you can see that E of Z satisfies the functional equation. So the functional equation, let's call it phi of U, is 1 over 1 minus D minus 1 times Z. Right? You plug E of Z into that, you get the result. Now this theorem tells you that if phi is nice, and that's as nice as you get, if phi is nice, then you did this little exercise in calculus and you should get some. So let's check if I can derive in front of everyone. So I forgot what's the, yeah. So we need to solve the following equation. So it's U times, you have two minuses, that's fine. This is the derivative, hopefully. And if you look at it for a second, this is a u, right? If you look at it for a second, this gets cancelled with that, like one of them, the other ones go there. So you get the 2ud minus 1 is 1. So tau, the solution, tau is already here, but the solution is 1 over 2d minus 1, which kind of starts to look good. But then what the theorem tells you is that you need to kind of plug it into phi prime. So phi prime of tau, if by the way is phi of tau divided by tau, kind of by definition here, it's easier to put it in phi. So phi of tau, if you plug this tau into phi, you get 1 divided by 1 minus a half, it's a 2, divided by tau, so it's a 4d minus 1, this is a 4, not a u. And this means by this theorem that the nth coefficient of E of z is 4d minus 1 roughly to the n. And for me, you have to go to d. D is the same thing as z, it's just a shift by 1. But the interesting part is that from d, you have to go to c. So you have to take the n over 2 foot. So this means that zn of c of z is that to n over 2, which is 2 square root of d minus 1 to the n. So that's kind of a way of getting it. And you would appreciate it more in situation in which you cannot solve this function equation. It's not a quadratic equation. Yeah, okay, so I think we'll stop here, but hopefully the message went through. Analytic combinatorics and free probability are, really good tools for even analyzing combinatorial constructions that we know and love. Thanks.
Okay, thank you very much. Maybe 1 or 2 quick questions, if any remain?
Very nice, but I have one confusion. So the odd or even depends on E or D. All the coefficients are 0, right?
Yes, or the other
Then
ones.
what does this really mean? So you're telling me that the coefficient, the nth coefficients of E of Z.
I should, right, you're right. I should separate the even and the odd ones, and that only works for the even ones. But yeah, I'm just not doing that.
But that means this theorem has some.
Right, there is a cyclic thing that you have to worry about. That's part of the nice. So in this sense, it's actually not nice. It shouldn't have cyclic. So you need to apply it to either to apply the more general theorem or to just do what I did. Like look at d of z squared, and there you're fine.
No point cycle.
Right. Yes, exactly. Cycle. I mean, the real problem is that you have poles with the same radius from 0. That's what.
Anything else?
So this functional equation or this theorem in particular says that any solution to such a functional equation has in the limit, the coefficients are just powers of a fixed number.
That's true.
This by itself.
By itself is interesting. That's true. And it tells you, the multiplicity of the poles with the same radius actually determines how accurate it is and so forth. Also, the type of singularity in the pole.
It's like when you just total recurrence equation.
Exactly.
Which is the same really, right? I mean,
That's true.
but you say the recurrence doesn't have to be linear.
Right.
Exactly. Recurrence, right? If you have finite recursion,
Right.
then the limit coefficient.
Right, like the Fibonacci, for example.
Fibonacci, for example.
Right.
And so it doesn't have to be linear.
That's true. It
And
doesn't.
in the linear case, the derivative
see
is a constant, but
Right.
okay.
And this is
So
a very
that's
strong. Yeah. You can actually write it in terms of the
proof
example.
this is complicated.
For who, right?
No, okay, so in the linear recursion
No,
case, we learned it in high school.
Right. No, you need all of complex analysis like 101 to do this. You need to do work with the residue theorem.
So But just for the consequence I'm talking about, not for the theorem, but just as it.
That's, I don't know, that's
I think
interesting.
that it doesn't follow by linearizing whatever field.
I don't know, that's a good question. I mean, I know the direct proof and it's kind of built on layers, and it could be hard to. But you really need like it's slightly more than a course in complex analysis, a standard course at least.
Yeah, but I'm trying to get a much.
Right, I know.
consequence.
Yeah, I know.
Just that.
Yeah, I'm not into it enough to give you a quick answer.
Okay,
Okay.
so thank you very much.
Oh, no.
Okay, let's have
Apologize.
one more question.
Do you believe that the transitivity of H is necessary for the?
No, it shouldn't be.
That's a consequence of the artifact of your proof.
Right. And experiments suggest it's not important at all, and it shouldn't be important, but then the recurrence relation is more complicated. You can actually form an automata that tells you, that kind of encodes H, and then there is a more general theorem that talks about if the function comes from a certain automata, then what happens. And we can analyze that for every graph that we want, but we couldn't analyze it for all graphs at once. But it's definitely us.
Thank you so much.
Thank you.